it says that almost over 30% of total energy is actually contributed or attributed to building sector, also producing a lot of CO2 emission. So we have now a strategic development goal towards smart cities, smart buildings with advanced materials. So which is actually directly linked to this United Nations Sustainable Development Goals, which is basically linked with this number 11 sustainable cities and communities. So this is the main motivation towards this work nowadays. So a lot of research work during the last decades on this phase change materials, which is incorporated in building or construction materials, towards this in a way for the new construction as well as passive retrofit solutions for the old buildings. So you can see one cartoon for this so-called micro encapsulated phase change materials embedded in some gypsum board material, which is usually applied in the interior side of the building. And we'll go into a little bit of detail on that. What is this terminologies? So our goal is actually to find mostly nowadays this environmentally friendly solutions, which is sustainable. And this is actually PCM or the phase change materials that is actually widely used in construction materials. So the basic idea behind this is actually which we link with this thermal energy storage principles, which is here it is actually latent heat based TES, thermal energy storage system idea. So here we use actually solid to liquid transition, this melting solidification cycles for a desired range of temperature that is related to this application that we're looking at. So in terms of indoor environment in this building that we are actually focused for this talk, is related to this solid liquid transition. So the operative temperature will be the melting point range is important parameter here, which is actually 19 to 26 degrees centigrade, which is the thermal comfort level while being inside an indoor environment. And as you can notice that this is inherently a transient process, so there will be a phase change, absorbing energy and moving to a transition to the liquid phase. It will absorb energy, and essentially it will try to reduce the load, the heating load, or if you move in the other way, it will be the cooling load and the heating load conversely. So the key idea here is that it essentially, when you use phase change materials, it requires less material, which is basically you can have material which is having much less thickness. So in this cartoon, in the right hand side, you basically see that this phase change materials incorporated in a wall board, which is equivalent to much thicker concrete wall and brick walls. So application of phase change materials in gypsum board is quite well established and used a lot. And although there are some cost issues involved here, we'll talk about some of the characteristics down the line. And so other than that, PCM is used in all sort of materials in building envelope. So here you see an indoor interior operational setup, where we see that in daytime operation, the PCM, which is actually, let's say, covered out inner layer of this, the outer surface of the indoor environment, which is actually gaining energy, and then it's converting to the liquid phase. And to have a proper cycle, it has to be recharged, so that in night time, it actually required to be cooled down to go to the solid phase, so that we can, again, the next day, we can reuse properly. So this nighttime operation, which is recharging of the phase change material, is quite important. So a lot of night ventilation strategies and other mechanical coolings are required often to actually recharge the phase change materials. So to have a proper cycle, this is important to actually change the phase back to the the original state that we are interested in. So this is a hot, or let's say the summertime example that we are looking at. So some of the characteristics that these are very important to look into, and in the right hand side I'm showing some of these classification of phase change materials. It's a huge domain. Phase change materials is used in many applications in many ways other than this indoor climate setup. So here we see that thermal, physical, chemical, environmental, economical, these are the key point of view that one should look into it towards the design and let's say optimization of or making the phase change materials. Because usually we design the phase change materials to attain certain range of operating temperature. So the melting point range is important with high specific heat and thermal conductivity and physical properties. Those are conducive towards the application that we're looking at. Of course, with other physical properties with high density and volume. I hear some noise a bit. Okay, now it's okay. So in terms of chemical point of view, we need to pay attention to specificity that it has to be non-toxic, and it also has to be fire retardant, so that this flammability is an important aspect towards the chemical stability, as well as the compatibility with the building materials. So in general, we'll make a cocktail of different compounds to make these advanced materials, so that we should pay attention towards these chemical properties. And of course, this is nowadays most important thing is that we have to be very responsible towards the environment, which is one of the key ideas worldwide to reduce as much as carbon footprint. So the environmental studies are always important towards this characterization of phase change materials. So it should have low impact toward its life cycle. So the life cycle analysis are also very important, and of course the cost. So often it appears that many research areas that those people are actually coming from the material scientists developing things which requires a lot of effort to make it commercially viable. So these economical aspects are actually very important to look into. So that's why it's written here in this small highlight that it is difficult to achieve all the qualities, because we're actually trying to optimize things with many perspectives. So as I mentioned, we're actually looking into this solid liquid transition. So this type of phase change materials are actually important for us in this building applications, and mostly more popular thing is actually organic or bio-based phase change materials, which is specifically paraffins, and these fatty acids are used in our applications. So salt hydrates and inorganic salt hydrates are also can operate in the range of building operating temperature. This you can see here in this cartoon, which is actually kind of converting this idea that this paraffin, fatty acids, and salt hydrates are in the operating range of that building applications. Here it's mentioned in this range. Here you see this the temperature range where the phase transition occurs is an important parameter. So, and it's actually plotted against phase transition enthalpy. So in general, this paraffin-based things are more popular because of several reasons in chemical aspects and availability and cost and other things taking into account. So this classification that you see on the right hand side is actually kind of linked with here that is with the building application, that what kind of phase change materials we should choose. So now we'll touch two important design issues before we go to see some practical examples that we perform with advanced materials in our laboratory. So one is actually containment, another is actually enhancement of the property. So in this slide, we basically see the containment, means that actually, since I mentioned before, we need to make a cocktail of compounds, which eventually gives these advanced materials for our applications. So it has to be this phase change will also go to this solid to liquid states of these compounds. So they should not contaminate with other constituents. So that is the key idea. So the leakage is also an important factor. And you see that there is a volume change, and it can create some air gap when there is a first phase change happens from, for example, liquid to solid. So to do that, usually what we do, we actually put PCM inside a container, and then you embed or mix with other compounds. So that the phase change is happening with a covered container. So this can be done in several ways. There are something called encapsulation technology behind this. So as we see here, this macro encapsulation, micro encapsulation, these are two main technology that is available for actually making or realizing the phase change materials for effective use in these advanced materials. So micro encapsulations are quite big in size, and it can be in sort of container which is rectangular or different types of shapes. This in the right hand side, you see that some sort of aluminum container where the phase change material is inside, and then it is used in application. So, but the thing is that it becomes bulky. So in most of the cases, for example, that gypsum board that I was talking about, usually this micro encapsulation technique is more viable and advantageous because it avoids this bulkiness. So the material scientists came up with this idea that one can put this phase change materials inside a polymeric shell. So it's like a spherical ball inside the PCM is sitting, and it is changing phase inside. So there are several ways one can produce these things. So there are a lot of work, a lot of research work is going on there. The apart from this micro encapsulation, this we call as MPCMs, and which is actually available in commercial products. But you see here in the right hand side, one of these a German company produced this MPCMs, which is actually used in many applications. And there are several other producers as well. Also, this shape stabilized phase change materials, in short we call SSPMs, is also not 100% in the commercial level. It's still in the research level. So here we actually keep a solid a combination of polymerization with different type of compounds, so that even though the phase is changing to the liquid phase for the phase change materials, overall it appears like as if there is no change in the state because of this shape stabilization with other compounds. So there are a lot of chemistry involved there, and there is some criteria that one has to take into account. Some of this is mentioned here. I'll not go into in detail in that. So please go to the references if you are interested in. So a lot of research work from the material scientists and chemistry people are focusing on these areas. But the thing is that apart from these containment issues, we need to put PCM in a container. We actually need to also pay attention to the physical and thermophysical properties and mechanical properties. So often the property enhancement is actually becomes important because these phase change materials usually have very low thermal conductivity. So this is the key property that usually we need to pay attention to increase the thermal conductivity, so that there will be a efficient way heat is transferring, so that the phase change is happening correctly based on our requirement. So often this kind of additives are actually required to have this enhancement of the thermal conductivity. So usually metals or let's say carbon-based compounds can be used in macro scale, bigger scales, or nowadays most popular things in research communities coming as nano additives. There are several nanotubes and other nanoparticles are used to enhance the thermal conductivity. So as you can imagine now, this field of research is quite vast, linking with the basic science with a lot of chemistry involved, as well as the engineers, those who are actually looking towards the actual realization of the commercialization of the product and making the benefit in terms of carbon footprint. So a long way to go to start from designing a phase materials which is very optimized. So a lot of optimization problems comes into picture. So essentially, this is the cooling and heating load that we can actually reduce to this phase materials. So as I mentioned before, it is used almost everywhere in the building setup. I'll show some of this idea about this phase materials incorporated, or let's say in terms of outer layer of the gypsum boards that we performed. But you can have a lot of description of products in this reference of J. Kosny, and it also mentioned very interestingly a lot of interesting patented compound that usually people are using in commercial products. So in terms of analyzing, mostly one has to do the experimental studies as well as numerical techniques are applied to towards finding optimal solutions. So as you can see in material levels, one can actually focus towards designing this micro and nano encapsulations as well nowadays with nano additives, with nano coatings. A lot of bonding interactions are involved there. And these characterizations of all these properties are important. But the building engineers like us, we are actually doing the room level and building level experiments. So these are also important to scale up things and making it viable and looking into this real benefit in terms of cost and in terms of energy benefit. So numerical approach, one can do this in material level. This coming from the particle approach, it means molecular dynamics with multi-scale modeling, and computational fluid dynamics can be also used to see the convective or movement of this liquid solid phase. So there are a lot of works in that direction as well. But in terms of real application, we need to actually come up to this room level and building level, where we usually use this building simulation tools like a bunch of things available here. For example, IDAIS, Francis Energy Plus, and all these tools are actually can handle zone-based temperature calculations with finding out eventually an energy budget and energy calculations in terms of room level and building level. And of course, this life cycle analysis, LCA, is of course very important for us to. So I think I'll show quickly some results that we performed here in Oslo Metropolitan University. This is actually coming up from another research with phase materials in concrete, and it came up with this company that we communicated with, Gyproc, Sweden. They actually developed this new spackling material. Spackling materials are materials usually applied in the surface to repair some defects, surface defects. So it's like a finishing coat outside the surfaces, especially the inner surfaces inside the room. So they actually made this MPCM, which is micro encapsulated phase materials with microplates, and which is basically a slurry, and then you can apply very easily. So the idea behind this thing is that making a board incorporated phase change materials is quite costly, which is actually the main drawback in terms of commercialization. So this idea actually they came up that well, instead of putting inside gypsum board or other materials, why not making coating material, which usually we do and can easily apply. So this is quite novel, and this is probably coming into the market soon. So this is actually done by two master students this last spring in 2020. This is our lab colleagues, and these two master students actually worked, and Gyproc actually helped us to build the whole thing. So we have this climate chamber, which is basically mimicking an office cubicle with a certain dimension, which is very realistic, although the height is slightly less than the normal setup. Usually 2.7 meter is the normal standard height, but this is a little less. And so we have this a door and a window, and all these surfaces, actually the wall surface and the ceiling, we covered. First we put gypsum board, and then we applied this spackling material, and then we studied a daily basis schedule, like as if we are simulating an office building with a business hour and non-business hour. So like a 5 days experiment. So what is there inside is basically two tables with as if two human beings, two occupants are there with a laptop or let's say a desktop machine, and we have some lights, and we have also solar gain through the windows. So these are actually simulated by these instruments and measured the temperature of, and the velocities inside, and we try to see the effect of with PCM and without PCM, how this thing is actually reducing the temperature. So typically a summer situation we solved here. So the idea was to investigate the impact of this phase change material based spackling material, which is applied on the surface, and we did some parametric study. We varied the thickness of the phase change materials, numerically solving this because it's not easy to change this and repeat these things with varying thickness. As well as we, the two important things we studied, we changed the ventilation rate as well as the temperature of this airflow. So as I mentioned, this nighttime cooling is important so that we can recharge the phase change materials efficiently. So this is just the cartoon of this room. As I mentioned, this is the window. This part is, you can ignore now. This is the chamber where we can have this side a specific temperature with some cold or hot airflow. So because we have this space section here. So for this experiment, we are not using that. We're basically making this office cubicle with and without PCM. And this is actually done with this wooden frame, and the gypsum boards are actually attached on this. And then we applied the phase change materials, which you see here. How come this guy from G-Prof is actually helping? Sorry, I cannot hear you.
Carry on,
okay.
Carry on.
Okay, so this is just, I'll quickly, if I'm running out of time, please let me know. So the thing is that here I quickly show some pre-processing of this. This is required to be kind of charred a little bit before using, and then this can be applied very easily, like as if you're applying paint. I'll just skip a little bit on this video so that you can see how this is being applied. So this is gypsum boards already attached, and the wooden frame, and then we apply these phase change materials. Sorry for this video because I was taking with my mobile, and yeah. So essentially, this spackling material, what it is basically again a cocktail of mixture of compounds with fillers and additives and binding agents, so that it can quickly or smoothly attach to the surfaces. It can be attached. It can be applied on other surfaces, not only on this kind of gypsum boards. It can be applied in other surfaces. But in this experiment, we have done that, and so you see that it requires the final touch, like the way we do. So you have this down in the final touch here. So then it becomes very smooth surface, like a coating. See, this is the way it is done here. This is the usual way of making cement masonry equipment. So I can stop this now. So you see here in this wall now is actually now applied this phase change materials. But one important thing is that, as I mentioned, this fire is, and flammability is an important thing. So one need to actually apply a fire retardant white coating paint. So this is actually the gypsum board, which is linked with this wooden frame, and this is the phase change materials with near about 2 millimeter. It appears a bit thick here, but we measured in random sampling that is actually in the range of 2 millimeter we applied. So in this setup, we actually applied around 100 kg of this phase change materials. So you see here, we actually cut out this thing. So once we have this dried, and this white paint, which is basically a fire retardant material incorporated there, which looks like white. And then this is actually the thickness that we are analyzing as phase change materials. So around 30 millimeter gypsum board, and then we apply this coating materials. So I'll just briefly touch this thing. Probably I already covered around 28 minutes. I should stop soon. So here actually as I mentioned, we actually mimicked 2 human being occupant, which is actually done by this ventilation ducts with black paint, and heating like bulbs and heating coils inside, heating panels. And also here you see this is the window that I showed at the beginning. So this is the door and this is the window. Here also we have heating panels, and which is basically mimicking the solar game. So we have actually a schedule, the business hours, morning 8 to 6, where you have a certain rise in this the solar gain, and it's falling, and then in the night it is basically non-business hours when we have actually different supply air temperatures. So these 2 supply air temperatures actually for indoor climate, the ventilation system with certain airflow, and then we actually made these experiments with and without PCM to have to find the effect. So here briefly we see that around 1 degree centigrade drop with the phase change materials here, which is actually during the daytime, and it starts 9 a.m. Actually, you see here this PCM is actually started working. It started melting. So the melting range is actually for this phase change material is actually near about 18 to 26. So it's actually reducing about 1.6 in the ceiling. So as you can see here, there's a little difference in the thickness in the surrounding walls and the ceiling. So we got a little bit better saving here, about 1.6 degree drop in temperature with this. So what we did after that, we actually also measured thermal conductivity of this material and tried to see whether the vendor what they measured with other groups is correct or not. So we did a hot box experiment to measure the thermal conductivity. But essentially, we did this parametric analysis with numerical calculations. So EIS, this is a business building simulation tool, which is actually used. The phase change materials wall model is there. One can incorporate this time-dependent CP, the thermal capacity, which is the most important thing here, as well as thermal conductivity. So we actually used a temperature dependent CP, which is provided and measured by this vendor, and we actually studies. And so this is the validation which gives confidence for us to do the parametric study. And this actually has been published in last Build Nordic conference here, building simulation community. And we see here the effects of this thickness, as well as the supply air temperature in night and supply air flow rate in night. So what we see here, you cannot keep on putting phase change materials so that you gain benefit. It means one could go to an optimum level because it has to be recharged. So what we see here, the drop in temperature in daytime, which is the red with no PCM and increasing PCM thickness. So you see this dropping, but it is becoming non-linear. So the reduction is becoming less. Also there is a little shift in the maximum temperature difference. For example, in 4 millimeter thickness, which is the highest thickness that we measured, is actually the drop is a bit around 6 o'clock. And so it's the later phase, the temperature drop is coming in the later afternoon. But for this 2 millimeter thickness, so this is arising from the fact that its PCM is actually having more. It is kind of shifting delaying the peak a little bit downward, so that the gap is actually appearing more. Also here you see in the night time, the temperature, which is actually in our base case was 14 degrees. So if we keep on increasing it, it's actually not suitable after certain temperature because the PCM is not properly recharged in those cases. So naturally we have this reduction of temperature, which is less in time when we have higher nighttime supply temperature. So ventilation is also important for nighttime charging. And we also looked into this air flow rate, which in our base case it's around 230 meter cube per hour. It means sufficiently cooling is done, which is basically this near with this magenta. So if you increase, naturally it will lower the temperature, and if you decrease the air fluoride, then naturally the cooling is not sufficient to recharge the thing. So we get more effect in the evening time, or sorry, morning time. In the morning time, we need to actually recharging. So, but the thing is that we with this preliminary study, we actually established that it has a lot of potential. So this spackling material is kind of interesting approach now. So this is almost in the market. I think this year they were supposed to be in the market. They're going towards the final stage of approval, I guess. And with this parametric study, you also doing numerical simulations with bigger building level with many offices, so that we can have more detailed energy budget. So this is under process. So in a nutshell, I'll stop here. We basically covered in a very shallow initial information that one can have to start with this phase changing materials in building applications. So as I mentioned, there are two important design issues, especially the containment and the property enhancement. And it's still a research, active research area for material scientists as well as engineers. And we can gain a lot of heating and cooling loads, so that essentially we can reach towards this United Nations goals and towards more sustainable and environmentally friendly solution for rapid urbanization. So I'd like to thank my colleagues, Tuarvid and Haptamu. These are my colleagues here. During the experiments, they took a lead because this field is really, really new to me. And the lab assistants, Oystein and Arns, they really helped us to fix many things in terms of from their enormous experience, hands-on experience by setting up this thing. So actually, it takes a lot of effort to make this experimental thing. Andreas and Chakri, these are the two master students who work with us, and Ebenezer and Hakon, these are the main guys who actually provided us with the material, actually free of cost. So I'd suggest, if some of you are actually starting, or if it is new to you, you can actually go through these 3 books. These are most exciting in a way to start and embark in this field. I'm also relatively new, so it helped me to build this talk as well. And we are actually interested to carry some other studies in this direction in our department. So this is the context. So you're happy to, I'll be happy to take some questions, and please be in touch if you are interested to do some collaboration. Thank you very much.
So in the chat box, we have one question.
How to, is this already shared, or now sharing is stopped or not?
Yes, sir, your sharing is up, but your screen is visible.
Okay, yeah, then it's fine now. It's okay. Yeah. So yeah, please carry on.
So what will be the added benefits while applying these PCMs in pharmaceuticals aspect or clean rooms?
Pharmaceutical.
Hello.
Yeah.
So actually my question is, you are making some materials which will either cool the room in summer days, or in winter days it is actually heating. I am from pharma background actually.
Okay, yeah.
So that is why I'm asking, sir, in pharma also we have to apply many kind of acrylic paints inside the clean room or manufacturing houses for easy cleaning, removal of microbes, and temperature maintenance, actually 25 degrees centigrade room temperature, or inside the vaccine freezers minus temperature has to be maintained. So will this be give some added benefits?
Actually, of course, definitely it's actually linked with this thermal control, let's say the indoor temperature control. So, but might not be this specific phase-changing materials one has to design. As I mentioned, the transition temperature is important. So the melting range has to be tuned. So the chemical cocktail can be actually tuned to go towards this the temperature range that you are looking at. So that will, in my opinion, that could definitely be helpful.
Because this will also help, because many things, suppose in the some areas like in India, in northern India, like in Viwari, in Rajasthan, or they are very hot, and some areas like in Baddi, they are cool. So for the many companies are seeking cool areas, so they will spending less amount of energy while maintaining these temperatures. But these things are getting costly high up in the mountainous areas. But if you can have some material which can just control this temperature in hot climates also, it will
Yeah.
also this promote the formation of many industrial areas in many hot climatic areas.
Yeah, actually, in fact, we basically studied the summer situations here in Nordic countries here as well. I mean, Oslo, which is Scandinavia. Here is actually really, we see that the global warming is happening. Summer is becoming hotter and hotter. And that's why we actually studied the cooling load reduction in summer conditions. So it is really applicable. But the main issue, as we noticed while restarting, or let's say rejuvenating this fission materials research, that the cost is the main barrier. Even some producers actually, they stopped making these things because of the high cost, especially this gypsum board that I was talking about, fission materials incorporated in this gypsum board. But that's why I think they have some research wings that are working on it, and that's why this GPROC Saint-Gobain, which is also having markets in India, I think, with ceilings and falls and fall ceilings and other things, because it's actually, Saint-Gobain is actually French name. So probably they have their headquarters in France, but they have this business in Nordic countries as well. So they came up with this, one of these research groups from Sweden, they came up with this idea that if you have this spackling material, which is relatively cheaper and easy to apply. So this could be an interesting point that you mentioned, Prasad. But since I'm not in a way highly let's say experienced in this domain, but it could be designed, in my opinion, and could be effectively used. Very good question.
So there is another one question. Manju MS, she just asked, sir, could you please explain the important characterization techniques for the micro encapsulated PCM?
Actually, it is not the top of my head because I'm not from the chemistry background, but we had noticed several research articles. You asked about the methodology?
Characterization techniques.
Yeah. Actually, this polymerization is an important thing here. So a lot of this hydrophilic and hydrophobic nature of this cocktail is important, actually. So the polymer scientist is actually working on that. So I do not have in-depth grasp in this, but in our research network, there is one professor from Oslo University, she's in our group actually. She's from that side, so she does a lot of chemistry-related studies. So if you're interested, I can give the link, and there are a lot of studies there. But as far as I remember, this segregation and this dispersion of particles when you make this cocktail is important, and this hydrophilic and hydrophobic nature is important to study there. But I cannot exactly tell the methodology. The polymerization is important there.
Okay, sir. No more questions are there in chat box. If there is any query, your mail ID has been shared, so they can just contact you. Thank you, sir, for your lecture, which you have delivered. It's most interesting. So I think if anybody is interested in this, then they can just contact you.
Yeah, we'll be very happy to collaborate, because this is a very open research field and a lot of things to do. We are just a baby here. At least I'm not in that expert level. So please communicate, and we will do these things as much as we can together. And thank you, Ashish sir.
Okay, sir. Thank you, sir.
Bye bye.